look at another class of functions called hyperbolic trigonometric functions. Hyperbolic trigonometric functions are defined as the variants of trigonometric functions: sine, cosine, tan, cosecant, secant, cotangent, etc. The sine hyperbolic function is defined as 1 by 2 of e to the power x minus e to the power minus x. In Mathematica or in Wolfram language, it is expressed as this expression sine h of x, and similarly the rest of the hyperbolic trigonometric functions. Cosecant hyperbolic is inverse of sine hyperbolic, secant hyperbolic is inverse of cos hyperbolic, cotangent hyperbolic is inverse of tan hyperbolic. So if you are not familiar with this function, this table gives you their definition and gives their usage in Mathematica or Wolfram language. So let's go ahead and look at the following problem. I want you to, for sine hyperbolic, secant hyperbolic, tan hyperbolic and cotangent hyperbolic, I want you to make the plots of these functions in some suitable range and identify the salient features such as extremas, zeros, divergences and asymptotes, discontinuities, and whether they are differentiable or not, and where they are differentiable and where they are not differentiable. So go ahead and play around with these 4 functions, plot them and identify these salient properties. Then I also want you to use manipulate command to explore the effects of parameter a in the functions sine hyperbolic of ax, secant hyperbolic of ax, tan hyperbolic of ax and cotangent hyperbolic of ax. Finally, I want you to compare the functions, the Lorentzian with a equal to 1 over x square plus 1, Gaussian e to the power minus x square and secant hyperbolic on the same plot. So the important question here is, what is the difference between them for large x? So I want you to try these problems by pausing the video and work them out as homework. I'm going to quickly demonstrate to you the last part of this problem by doing a plot. So I'll plot the Gaussian, the Lorentzian, and the last function I want to plot is secant hyperbolic. Interestingly enough, all these 3 functions behave the same way. So here is plot of all the 3 functions. It's interesting to note that all the 3 functions have very similar behavior near x equal to 0. In fact, that behavior is same as 1 over minus x square, and I can fix the plot range. That's just 0 to 1. It's interesting to note that all the 3 functions behave the same way near x equal to 0, but they fall off differently as x goes to plus infinity or x goes to minus infinity. Let's increase the range in which we are plotting to see that behavior. It's quite interesting to note that the Gaussian, which is represented by the dashed line over here, falls off the fastest. The Lorentzian appears to fall off faster than secant hyperbolic, but eventually secant hyperbolic takes over and falls off faster than Lorentzian. You can increase the range further and verify that secant hyperbolic represented by the dotted line is falling off faster than the Lorentzian. The reason is simply because secant hyperbolic goes like e to the power minus x for large x, while Lorentzian goes like 1 over x square for large x, and exponential falls off faster than 1 over x square. Gaussian goes like e to the power minus x square, so it falls off faster than e to the power minus x, and that is why the Gaussian function dies off the fastest among all of these curves. Let's go to the next slide. Let's talk about the vector fields, and let's understand how to plot vector fields and how to understand these plots. Vector fields are defined as n tuple. In 3 dimensions there are 3 tuple, they have 3 components, each of the component is a function of the coordinates x, y and z. So if V is a vector field, it's a function of x, y and z, it's a vector function of x, y and z, that is it has got 3 coordinates Vx, Vy and Vz, and each of the 3 components Vx, Vy and Vz are functions of the coordinates x, y and z. So a vector field has 3 components Vx, Vy and Vz, and each of them is a function of 3 coordinates x, y and z. You can also represent a vector field with a vector in terms of coordinate r, like in this expression. You can also represent vector field in vector notation as Vx I hat plus Vy j hat plus Vz k hat, where Vx, Vy and Vz are all three of them are functions of the coordinate r. In 2 dimensions, this simply reduces down to Vx I hat plus Vy j hat, and you can also go ahead and generalize the vector fields in n dimensions, but plotting something in n dimensions will be extremely difficult, so we will just explore 2 dimensions and 3 dimensions in this lecture. Okay, let's go ahead with the first example. In this first example, I want you to consider 3 vector fields v, u and w. V is x I hat plus y j hat, u is y I hat plus x j hat, and w is minus y I hat plus x j hat. I want you to calculate divergence and curl for these 3 vector fields. So if you want, at this point you can pause the video and calculate the divergence and curl for these 3 simple vector fields. Once you have calculated divergence, I want you to create a vector plot and verify the results, what you found out about the divergence and curl. And finally, I will demonstrate to you that these vector fields represent flow of a fluid, and will make a streamline plot to demonstrate that to you. So let's go ahead and check the answer. If you calculate the curl and the divergence for V, U and W, this is what you're going to get. V has a non-zero divergence of V is 2, but curl of V is 0. On the other hand, U has both its divergence and curl vanishing, and W has 0 divergence but non-zero curl pointing in the k hat direction, that is perpendicular to I hat and j hat. Let us see how these 3 fields appear different when I do a vector plot. That is, if I make a vector plot of these 3 vector fields. What does it mean to have a vector field to have a divergence but no curl? What does it mean for a vector field to have curl but no divergence? What does it mean for a vector field to have neither divergence nor curl? Let's explore it by plotting these 3 examples. So in Mathematica, in order to plot this, we'll use this by invoking a function called vector plot. And to do so, we'll need to represent the vector field as a 2 tuple or a 3 tuple, depending on we are working in 2 dimensions or 3 dimensions. So in this case, my vector fields are xy, yx and minus yx in the flower brackets. So that's how we'll represent them in Mathematica, and we'll make a vector plot by invoking the vector plot function. So let me demonstrate that to you. There's my vector field xy. I have given its first argument, that is the range. The first argument is the vector field itself, which is 2 tuple x comma y. The second argument is the range of x, and the third argument is range of y. When I make a plot of this, I get a plot like this, where you see that in the center I have got nothing, and then I have got very tiny vectors pointing outwards, and then the length of those vectors increase and keeps on increasing as I go radially outwards. What does this mean for the divergence and the curl? Clearly this vector field has a divergence because something is diverging out of a volume. So if I create a volume over here, think of an imaginary volume, I see that something is coming out of that volume. That means that this vector field has a divergence. In fact, locally, anywhere you make a small volume or a small circle, you see whatever is going in, more is coming out of that. So less is going in but more is coming out. That means this vector field is divergence. In fact, it has divergence everywhere and the divergence is constant. In this case, divergence of V is 2. This has no curl because there is no sense of rotation in this vector field. From this plot, it's clear that this vector field is diverging out, but there is no sense of rotation. Let's go ahead and check this for another example for vector field u. For that, we can simply go ahead and plot vector field u by exchanging the coordinates here. Vector field u is y comma x. So when I plot that, I get something like this. This is an interesting vector field. You see that there are two special lines. Along this diagonal line, flow is inwards, and along this diagonal line, flow is outwards, and in between the flow is from this line towards that line. So over here in the center, we have what we call as a saddle point. If you are exactly on this line, the flow will take you to the saddle point, but if you are exactly on this line, it will take you away from the saddle point. For all the others, you will eventually end up going away from the saddle point, and you will flow towards this line, which is the line of stability, the line of instability. This is the line of stability, and this diagonal is the line of instability. As you, for all the for any other point, the vector fields are always taking you towards the direction of line of instability. Therefore, this field neither has a divergence nor has a curl. To see that, imagine drawing a small volume anywhere. If I draw a small volume somewhere around here, you see that whatever goes in, equal amount comes out, and as a consequence, this has no divergence. It also has no sense of rotation, as for any small volume, flow is coming in and going out, but there is no sense of rotation. Therefore, it also has a zero curl. Let's go ahead and check out the third example, w equal to minus y comma x. For this vector field, there is a clear sense of rotation. When I make a plot of this, I get something like this. There is a clear sense of rotation. If I make a small volume anywhere, it gives you a sense of rotation in the clockwise direction. Overall also, it gives you a sense of rotation in the counterclockwise direction. If you make a small volume, you will see there is a sense of rotation in the counterclockwise direction. But there is no net flow in or net flow out, therefore there is no divergence. So it has got divergence equal to 0 everywhere, but it has got a sense of curl or sense of rotation no matter where you are. Always the outside vector fields in any volume are bigger compared to the vector fields towards the inside, and that is why there is a sense of rotation in this volume. And as a consequence, this vector field has a non-zero curl while it has a zero divergence. We can also look at this by using a streamline plot or stream plot. I can plot a vector field as a vector plot, and sometimes it is useful to also plot as a stream plot. So rather than doing a vector plot over here, if I replace this vector plot by a stream plot as done over here, I will get a plot like this, which is quite similar to the plot that I have got over here, except the length of the vectors were getting bigger and bigger, which was saying that the strength of the vector field is becoming bigger and bigger as I go outwards. But for the stream plot, the length of the vector is ignored and straight lines are drawn showing the direction of the flow. So stream plot does not care about the length of the vectors, it simply draws all vectors of equal length, showing you simply in which direction the flow is. So for a fluid flow, electric field lines, magnetic field lines, a stream plot is a useful way of demonstrating than a vector plot. In this case, you see there's something funny business happening in the center. That is, in the center, the stream plot function is not able to plot very clearly what's exactly happening over here, and that is because over here it's very difficult for the because x and y both vanish, the sense of direction is not clear. As soon as you go away from that, sense of direction is readily outward, but at x equal to 0, the sense of direction is not clear. In fact, vector field is vanishing at that point. In order to avoid such a situation, we can do a small trick. We can we can apply an option called region function on the stream plot. Region function is given by this particular line of code. At first it may appear something complicated, but you just have to understand its usage, which is very simple. So you define the region function, tells you in what region you should plot, you should make the stream plot, and what region you should exclude. In this case, it has you define the region function as a function which has 5 arguments: x, y, the x component of the vector field, the y component of the vector field, and the norm of the vector field, and then you specify a condition on these 5 components. So in this case, I have given a condition that x square plus y square is greater than 0.05. That means make the vector plot only in the region where x square plus y square is greater than 0.05. I have completely ignored what's happening with these other 3 quantities, and as a consequence, the vector field is the stream plot is only drawn for the region x square plus y square greater than 0.05. As a consequence, there's nothing over here. That avoids the problem that we are seeing in this plot, where it was unclear what's happening at the center over here, and that makes the plot looks nicer. Okay, we can go ahead and play around with this, and we can make this 0.1, which will make this region bigger, and we can make it slightly more bigger, maybe 0.4. We can also do something else, for example, depending on your need, but just to play around with it, I want to demonstrate to you that we can also say that n is greater than some number like 0.1. That is, if the norm is greater than 0.1, norm means square root of vx square plus vy square. If norm is greater than 1, only then you plot, and that also avoids certain region. I can go ahead and make it slightly bigger, and that also does the same job effectively. All right, you can go ahead and play a little bit more with this. If you wanted to only plot for certain for positive values of Vx, the x component of the vector field, you'll see that the plot will only be made for the positive values of the vector field. And if you wanted to add another condition to it, that v of x or norm should be greater than 0.5, let's make it even bigger, 1, you can get a plot like that. So go ahead and play around with that. If sometimes you want that on the stream plot, you also want to see the length of the vectors, you can use something called a stream density plot. Stream density plot function works exactly like stream plot, except that it also plots the density according to the length of the vectors. So density, it will plot a grayscale density as for example in this case, as the vectors become longer and longer, or the vectors become more stronger and stronger, it's more white, and as the vectors are weaker and weaker, it shows you a black color. Apart from that, stream density plot and stream plot work exactly the same way. Stream density plot is sometimes useful to show the strength of the vector field. Let's go ahead and look at a 3-dimensional example of vector field. Here are 2 vector fields, v and w. V is xi hat plus yj hat plus zk hat, and w is minus yi hat plus xj hat plus zk hat. Let's go ahead and make a vector plot of this in 3 dimensions. So the first vector field is simply the 3 components are x, y, and z. So I put the 3 components x, y, and z. Use the function vector plot 3D because I want to make a 3D plot. Give the ranges of x coordinate, y coordinate, and z coordinate, and I go ahead and plot it. I have also given an option vector scale equal to 0.06. You can go around and play with it. You see, if I make it too big, the arrowhead becomes really big, so I can fine tune that by choosing it to be of the right size. You can go ahead and rotate this, and you can see what kind of vector field this is. Again, this is a vector field which has divergence everywhere. Let's go ahead and plot the second vector field by changing the x coordinate to minus y, y coordinate to x, and leave the third coordinate as z, and there we go. We get a field which has got some sense of curling around. In fact, if you align yourself with the z axis, you will see that this is going to have a sense of curling. The projection of the x and y plane is a vector field which is minus y comma x, something that has a curl. So when I align myself with the z axis, that z axis is pointing out, you see a sense of curl, a sense of rotation in this vector field. So go ahead and play around with vector plot and vector plot 3D and Streamline for some of your own examples. Let's apply this understanding or knowledge of vector fields and streamline plots that we have just learned to electrodynamics or electromagnetism, where we study field lines and equipotential surfaces. So in this example, we learn to plot the field lines and equipotential surfaces. Now, as you all know, that the electric field for a point charge located at a point RQ is given by this expression, q by 4 pi epsilon naught, which is the overall constant. The direction of the electric field is r minus rq. Rq is the point where the charge particle is placed, divided by r minus rq whole cube. That is that is something you have seen in some course on electromagnetism or in some book on electromagnetism. That is the electric field for a point charge at an arbitrary point r. The potential for the same is given by this expression, where the potential goes like 1 over mod of r minus rq multiplied by this constant q by 4 pi epsilon naught. Alright, let's go ahead and plot streamlines for this electric field. In order to do that, we will make use of streamline plot, stream plot, and this electric field goes like r by r cube, where we have vector r in the numerator and r cube in the denominator. Let's take the charge particle to be placed at origin. So then we have got vector r divided by r cube, which is simply x and y. Will do this in 2 dimensions, divided by x square plus y square whole cubed, and similarly for this for y. Let's set the range for x from minus 5 to 5 and set the range for y from minus 5 to 5. Let's go ahead and make the stream plot, and you see that the electric field lines are going outwards. Again, we have got some funny business happening at the origin. For this, I can go ahead and use the region function option and set that to function of x, y, vx, vy, and n, and let the function be such that n is greater than 0.1. Yeah, bigger value. We have to go to n less than, let's say, 1. There we go. So that's a example of electric field lines for a single charge particle, where the charge particle is placed at origin. Let's take an example of a dipole, an electric dipole. Now, if I consider the electric dipole made up of 2 charges plus q and minus q placed at origin, so plus q is placed at origin and minus q placed at a0, that is on the x-axis at distance a away from the origin. The electric field for this setup is given by electric field because of the positive charge and electric field because of the negative charge. The positive charge is placed at r equal to 0, so therefore it's given by r cube, while the negative charge is placed at r equal to a, therefore its field is given by r minus a I hat divided by r minus a I hat whole cube. We need to non-dimensionalize this electric field so that we can actually plot it. In order to non-dimensionalize, we are going to divide r by a and electric field by q by 4 pi epsilon naught a square, because the dimensions of electric field are given by q by 4 pi epsilon naught a square. Doing that, we simply get r by a divided by r by a whole cube and r by a minus I hat, r by a minus I hat whole cube. Taking r by a as x by a, y by a, etc., I get the following components for the non-dimensionalized electric field, where x is x by a and y is the y component of r divided by a. So you can verify that for the x component of the electric field, I get this expression, where x by square root of x square plus y square is coming from this part of the expression, and x minus 1 by square root of x minus 1 square plus y square is coming from this part of the expression. Similarly for the y component. So therefore, this is my vector field that I want to plot. In order to plot this vector field, I have encoded the expression over here. To avoid typing this expression again and again, I have used the replacement rules over here, which says that r is to be replaced with x square plus y square and r1 is to be replaced with x minus 1 whole square plus y square. So therefore, my vector field becomes x by r cube minus x minus 1 divided by r1 cube and y by r cube minus y divided by r1 cube. In order to type this arrow key, all you have to do is type the dash key and then the greater than sign and type anything after that. This turns into an arrow. Slash dot is used for a replacement rule. So this is the replacement rule over here. I'm making a replacement in the previous expression over here, with r goes to square root of x square plus y square and r1 goes to this expression. Slash dot says that apply this replacement rule onto this previous expression. I define the range of x from minus 1 to 2 and range of y from minus 2 to 2, and I also apply the region function, and I can, rather than choosing this complicated region function, we can choose a simpler region function such as n less than 5, maybe even bigger, maybe even bigger. There we go. We have got the electric field lines for electric dipole, where the plus q charge is placed at this point and minus q charge is placed at this point. The electric field lines are moving from plus q charges to the minus q charges. The norm less than 20 just make sure that the region plot is drawn only for the stream plot is drawn only for the region where the norm of the electric fields is less than the value of 20. We can make it even for higher, as long as we don't try to draw in this region where the directions is ill-defined. It's perfectly fine. So here, this was an example of electric field lines for a dipole. Now I can also work out the potential for the dipole, and non-dimensionalizing in the similar way, I've got potential for the dipole as q by 4 pi epsilon 1 by r minus q by 4 pi epsilon 1 by mod of r minus a I hat. Non-dimensionalizing this expression in the same way as I did for electric field, except for potential I am going to divide by q by 4 pi epsilon a, which is the dimension of the potential. Then I am left with 1 by r by a minus 1 by r by a minus I hat magnitude. Convert this into the dimensionless coordinates x and y. We are left with this expression. V is a scalar function. Now we want to plot this scalar function, but this time we want to plot contours for this scalar function. In order to do the contours, I am going to use the contour plot. And this time for the contour plot, I have got simply 1 by r minus 1 by r1 for the non-dimensionalized coordinates. So 1 by r minus 1 by r1, I substitute r with square root of x square plus y square and r1 for x minus 1 square plus y square. So let me go ahead and execute the contour plot. when I draw the contour plot, I get this particular function. Now this is my these contours show the equipotential lines. Contour plot means that I am drawing a contour for all the points for which v of r is constant. So these contours corresponds to various values of v of r. For example, this contour corresponds to v of r equal to minus 0.5. This corresponds to v of r equal to minus 1. This corresponds to minus 1.5, and so on. On this side, I've got positive values v of r equal to 0.5, v of r equal to 1, v of r equal to 1.5, and so on. This is my these contours are showing my equipotential surfaces or lines of contours of equipotential. Over here, I've got stream plot for or electric field lines plot for the dipole, which I have defined as field lines. This plot is called field lines because I have to the variable field lines I have assigned the value of this plot. So let me go ahead and execute this again. For contour plot for equipotentials, I have assigned it to a variable called equipotential, and when I lay over these on top of each other using the show function, show equipotential comma field lines, I can plot them on top of each other, and when I do that, I get this very interesting plot where I've got a plus charge over here, minus charge over here, and this plot is showing you both the equipotential lines and the field lines and the relative orientation of them. You can verify that equipotential contours are perpendicular to the electric field lines at all points. So for example, for this contour, you see the electric field lines enter or cross this contour at 90-degree angles, and similarly on this side, which is what we have learned in electromagnetism, that the equipotential lines are always perpendicular to the electric fields, and here by visual aid we can verify this directly. That will be all for today, and we'll continue with more interesting things next time.